All right, then on with question 2. And this is a pretty recognizable setup. Investigating the relationship between force and acceleration. So we've got a trolley, string, pulley, masses. So Fatima is making measurements to get acceleration with different numbers of discs hanging from the string. Spare discs, the ones that aren't on the string, are put on top of the trolley so that the mass stays constant. That's fine. Plots acceleration against hanging mass on the grid opposite. There we go. Okay. And yep, explain why A is to be related to M and M by the equation as follows. So this is an F equals MA practical. So I think all we need to do here, there's only one mark available, is state that F equals MA, and the force here, the accelerating force, is equal to mg. Arguably, I would have been better putting in an uppercase M there, because it's the total system mass that's involved there. We're not going to have to do much here for 1 mark, really, are we? So MA equals mg. I think that's probably enough, obviously. That rearranges for what they want. Use the graph, determine the mass of the system along with the absolute uncertainty. Okay, so yeah, the first thing to note here is the gradient of this graph. This is an acceleration versus mass graph, so the gradient is going to be equal to g over m. That is the first thing to note. To get that gradient, given that we're after an absolute uncertainty, we're going to need lines of worst fit. Now look at this question. Absolute uncertainty we're after, and this is 6 marks. It's a lot of marks. That's the same as a QER question. But unlike a QER, we can guarantee getting these marks. We know what calculations to do, so we can definitely get the marks. In a QER, you can never guarantee 6 marks. So let's plot our lines of worst fit. And remember, with lines of worst fit, they must still fit. So they must go through all of the points. You can't have a line of worst fit that doesn't go through all of your error bars. Sorry, not points. So if I start from up there and drop it to down here, that's going to be my steepest line. I'm just going to draw 2 lines with the pen here, and then I'll fiddle about with them with the mouse. And then I want shallowest possible line. So the rules are, my lines have to go through all of the error bars, and be careful with that, because it can be pretty tempting to just kind of go from the top of the leftmost point to the bottom of the rightmost error bar. But if we look in this case, that's actually outside of this error bar, so that line is not going to cut it. So this line needs to be inside of that. So I'll just move that up until it is, so somewhere about there. And my other line, if I adjust that so that it actually is inside all of the error bars, I think it's going to be okay. So it is actually just going to go from the bottom of the leftmost to the top of the rightmost. But yeah, just check that both of your lines, max and min, are inside that. So then our next step, max gradient equals, and then min gradient. So we'll do max and min, and then we'll take a mean, and our absolute uncertainty will be half of the range between max and min. So let's have a look. The best thing to do in these types of questions is always to really clearly label up the graph with the construct, where you've taken the gradient from. So I'm going to choose that line. Whoops, that isn't actually on the line. That's pretty annoying. This is a really fiddly thing to be trying to do with a mouse. So let me just stick that on there, and ideally let's make it actually vertical. And I'm going to come down to, yeah, I think that major grid line looks okay to there. And let's get a second line then across. And this is my shallowest possible line. So across to there. And then I'm going to go ahead and write on it my sort of delta y, delta x. So this is delta m. Where is that from into? 0.68. And over here 0.16. So 0.68 minus 0.16, 0.52. And then delta A is equal to, and that's going from 1 up to, just always be careful with your scale here, 4.15, so 3.15. And then the same thing for my max gradient. Let's get a line. So I'm just going to choose somewhere where it conveniently crosses a grid line. And bear in mind, to the nearest grid line is always fine, to the nearest minor grid line. You don't have to get super fancy about this and start trying to split minor grid lines or anything like that. So as long as it's pretty close to an intersection, that's going to be okay. So I'll go there, and yep, another line, and coming down to here for my max. Okay, so that end and that end, and again, yeah, delta m here. That's gone from this. Oh, I can't actually see the scale. That's gone from this point, which is 0.62, to 0.12. So that's 0.50, and delta A 4.0 and 0.675, 0.75, so 3.25. So that is plenty of evidence as to where I've got my lines from. So that is going to be worth, a reasonable chunk of these marks. It is time consuming, but bear in mind, so is a 6-mark QER. So this maximum gradient, then that steepest one. Oh, look what I've done. I'm an idiot. Why did nobody point that out to me? Oh, because you can't, this is recorded. Yeah, that wants to come down to meet the steepest line. Yeah, don't do that, guys. Don't be that person. So it's actually, that's actually 0.30 then, is it? 3.30, is that right? Let me just check. That's 0.5, 0.6, 0.65. So 3.35. Okay. Sorry about that. Yeah, so where was I? Max gradient then is delta A over delta M, 3.35 over 0.5. Equals 6.70. And minimum gradient, this shallowest line, 3.15 over 0.52. Can't quite manage that one in my head, I'm afraid. So 3.15 divided by 0.52 gives me 6.06. So M is what we're after, the mass of the system. So that gives me, this will be my minimum M, and this will be my maximum M, therefore. So 9.81 over 6.70 1.46, and then maximum 9.81 divided by 6.06, 1.62. So therefore, is the mean of these two, max plus min over 2, plus or minus half the range, so max minus min over 2. So 1.62, 1.54 then, plus or minus 0.08. Whoops. Now, what you would do just before you finalize your answer, this is actually fine the way it's worked out. Just check that you give your absolute uncertainty to one significant figure and then match that number of decimal places over here. So if 1 sig fig puts this in the second decimal place, this should go to 2 dp as well. So they should, the uncertainty and the value should have the same number of decimal places, and the uncertainty should only ever be to 1 sig fig if it's an absolute uncertainty. So that seems okay. Final part of this question then, describe the measurements and calculations that Fatima might have made to determine the acceleration to not consider uncertainties. So yeah, you've done this is a specified practical. It's the F equals MA practical. All different ways to do it. You could do this with light gates if you wished in order to do the timing, or you can just do it with a stopwatch. Let's have a look at the actual wording. Describe measurements and calculations might have made. So there's scope in this question for there to be a variety of different methods. I'm just going to use the stopwatch method. So we would just use a stopwatch to time the trolley from rest over measured distance. D. Maybe arguably mention that measured distance D, well, if I just change that to over a distance D measured with meter stick. I don't know if that's necessary to give the measurement equipment, but it's not going to do any harm, is it? So it says describe the measurements. So we've used the stopwatch to time the trolley from rest over a distance D measured with meter sticks. Those are the measurements, and then we need to mention the calculations necessary. So x equals, you need to use a suvat to turn that into an acceleration, don't you? Therefore, since u is from rest, so u is 0, therefore acceleration would be equal to 2d divided by t squared. And I suspect that gets all the marks. Okay.